Hello, my name is Carl Yukich, and this is Lab 2 of Physics 2211. For our introduction, the purpose of this lab is to observe the motion of an object dropped from rest that is capable of a noticeable drag force and compare it to two different computation models, one with drag and one without. Fundamentals of this lab include the concept of Newton's second law, more specifically the observation of forces of gravity and drag. And the brief result is that this lab showed the effects of drag can be extremely noticeable when compared to a model where only gravity will act on an object. Main ideas of this lab include Newton's second law, where acceleration, net external force, are directly proportional, where acceleration is inversely proportional with mass. And that's just fancy for F equals ma. When integrated force with respect to time in terms of the kinematics equation, you get v final equals v initial plus F over m to get acceleration with delta t, and just how acceleration affects velocity. Force of gravity is the force between two objects with mass. On Earth, the value of acceleration for an object dropped on its surface is 9.8 meters per second squared. And the equation for this lab is Fg equals negative m times g times j hat, where j hat is just the vertical direction going upward, and it's negative because in this lab gravity is acting downward. Force of drag is the force of air pushing on a moving object as a function of its speed. This model is force of drag is equal to negative b magnitude of velocity squared times v hat, where b is a proportionality constant that differs between any object, and v hat is just the direction of the velocity, which will be down in this lab. And terminal velocity is when the object reaches a certain speed, where the force of drag and the force of gravity cancel out to a net force of zero. That does not mean that the object stops moving; it just stops accelerating. In this experiment, the system is a crumpled paper towel ball up here, and the surroundings include everything else, including the air, earth, and floor. Initial conditions is that the ball starts at about a height of 1.9 meters. This illustration says 1.8, but that's at the bottom of the paper towel. The center of the mass starts more at 1.9, and it has no initial velocity, meaning it starts at rest. And here we see the drop, and it's just modeled in tracker going down. And early on, you can even see how this graph slope begins to even out at the end. We'll get to that later. For our code without drag, here we see the self-visualization. Our ball mass is set to 2 grams or 0.02 kilograms. Our initial position is 1.89 meters with no initial velocity. 1 out of 60 for delta t because 60 frames per second. Gravity is 9.8 meters per second squared, and j hat is our upward defining vector. For the calculations, we have F net is just F of gravity, modeled in negative g times ball m. Our ball velocity is updated with F net over mass to get acceleration, and position is updated with the changing velocity. Here we can see the model in action. Force of gravity is constant, position and time graph. For code with drag, all visualization, this is all the same except for a proportionality constant, which is set to 0.0017 for the proportional constant of the magnitude of the drag force just for this paper towel, different for every object. For our calculation loop, you can see our F net has changed because we have to include gravity and drag. Gravity is the same, and the drag equation is the same one as above. This just means squared, negative j hat, but it's also negative direction, so this means it's going to go up. Same bottom parts, just for clarification. These arrows are just this force multiplied by 25, just for visualization's sake. Here's the model. We can see force of gravity is constant. That drag force is changing. Our position for this time graph. If we go back one more time and we slowly pause, you can see how this drag force is slowly increasing. This is due to the changing velocity and how the equation is proportional with that changing velocity. So for our simulators, we see our graph of no drag has a constant acceleration, and if dropped in real life, would have plummeted through the floor compared to our observed. So we can see it would have gone through the floor at 0.6 seconds versus in our real life example, it stops at 0.783. Our observed and yes drag graph, which is our computational model with drag, seems to have an acceleration that approaches zero, as seen with the almost straight slope after 0.04 seconds. And our source of error, incorrect tracker placements, other forces like wind from an AC could be in play, and human error on drop and measurement of height. Questions and conclusions. Examine the velocity versus time predicted by your models with and without drag. Which model, if any, predicted terminal velocity? This is what we talked about earlier, and we're just talking about how the graph seems to even out at the end there. We can see the closest model to predict this is the drag computation model, but even this model is ever so slightly off. As you can see in the graph listed here, it never stops having some curvature. So this is the velocity versus time graph. You can see how this graph wants to start approaching and be constant at roughly 3.4, but it always has a curve and it doesn't seem to even out. For our next question, imagine that the object was initially thrown downward. Would the terminal velocity in this case be the same or different from the case where the same object was initially dropped from rest? So to answer this, by adding the drag model code to have initial velocity of negative 3.3 meters per second, we can see how the speed seems to infinitely approach negative 3.4 meters per second, but doesn't ever seem to get there. But this doesn't mean really anything in terms of the question. This terminal velocity would be the same as the ball dropped from rest. So the drag forces only depend on speed, not time. If we had another 5 meters of height for both cases, they would both reach the same velocity. So basically, layman's terms, this ball, same mass, same height, it's always going to approach the same terminal velocity because it has the same proportionality constant in the drag force. So it's always, if we had 5 extra meters of drop, it would eventually reach somewhere between this negative 3.39 and negative 3.4 meters per second. It would stay there. Doesn't matter if we drop it from rest, if we throw it upwards, if we pelt it downwards. Even if we pelt it downwards, past -3.4, it would actually slow down, because if you go back to the code and edit this to have like a -5 meters per second initial, this graph would go up because the ball would start slowing down as the force of drag is overpowering force of gravity, and this velocity of time would actually go up like this.